minutes late. I was busy here with your colleagues. So this afternoon, what I prepare to present to you is about Raman spectroscopy. Sir Raman is well known in China, of course. And it is very interesting, such a spectroscopy. It was, let's say, invented so many years ago. And if you look in time, the number of publications is still going up. Going up. Very interesting. Simply because a very important fact about Raman spectroscopy. Everything except vacuum, everything you can extract a Raman spectrum. So what is the difference is that in recent times we found ways to enhance very much the signal, the Raman signal you can extract. And this made a strong difference, a big difference. So, and also people learn because you can enhance orders of magnitude, really orders of magnitude, 6, 9 orders of magnitude, the signal you can extract. Then you can use Raman spectroscopy in a broad area of applications. And lately, especially in the biological and biomedical field, and it seems that this trend is going to keep moving on. Still many applications to come. Okay, we do a lot of, part of our experiments in our facility in Brasilia, we do Raman spectroscopy. We start doing that maybe between 15 and 20 years ago. And I will show some data about this. Okay, so here is Raman spectroscopy, and I'll try to cover this agenda. This is the man you well know better than me. And the Raman effect, it is related to the fact that any material can absorb electromagnetic radiation. Of course, you have to be in the right wavelength. But Raman has to do with atom vibration. Those vibration atoms could be in a gas phase or liquid or in a solid. So whatever you have atom vibration, you have a chance to do Raman spectroscopy, right? So it has to do with the energy of this vibration. Okay, so it has to do then with phonons actually. So let's see, if you illuminate your sample in this frequency, and then you can excite, this sample can absorb this energy, this photon. And then when the system comes from the excited state to ground state, it may create one phonon. So part of that energy goes to the phonon. And then the light that you can see coming out of the system. So you have light absorbed, and then that light is scattered. But the wavelength is different. So it may happen to situations. The energy that comes in and the energy that comes out, this that comes out usually is smaller in energy. That difference was used to excite phonons. Phonons means excite this vibration only. So part of that incoming energy is used to excite this vibration. This is the most likely situation. And it's called Stokes interaction. It may happen that the energy that comes in and the energy that comes out, but the one that comes out is higher in energy. It means some energy were given to the light that comes in. In other words, the light that comes in extracts some energy from the system. Who gave the energy? Again, phonon. Okay? So this is called anti-Stokes scattering. And then that's the case. You have Stokes Raman and anti-Stokes Raman. This shift between the incident light and the refracted light, the scattered light, is the energy corresponding to the phonon. Okay? Now, you can see the light comes in, just excite the system, bring in the system to an upper state, we call virtual state actually, and then when the system returns down, it generates one phonon. And if the incident light goes to the sample and returns without any change, actually we're not talking about Raman scattering. We're talking about Rayleigh scattering. Okay. This is the case. I'm sorry. This is the anti-Stokes case actually. So you excite the system and you get more energy. You take energy from the phonon. And this is the case. You excite the system and the light that comes out is lower in energy. The difference is given to the phonon system of your sample. So you have these two situations. And every phonon generated, any kind of binding between atoms, they have their typical vibration. That vibration is a sort of fingerprinting of the molecule or the combination of atoms. So you can use this typical energy of vibration to identify materials. So this phenomenon was then used to build what we call Raman spectroscopy. So one thing is the Raman effect. The other thing is the Raman spectroscopy. You can use the Raman effect to extract information about materials. Then what you have is Raman spectroscopy. Typically, instrumentation for Raman, it requires that your sample is illuminated. So, in the old times, it was more difficult because sources of light were only lamps. And then it was a big step in Raman spectroscopy when people discover the laser. So the high intensity provided by the laser gave a new breadth to the Raman spectroscopy. Make Raman spectroscopy a big jump. And that was in the 60s. So laser was, as far as I remember, laser was invented in New York City, Columbia University, right at the border of the Central Park. Then, after laser came in, so Raman spectroscopy just jumped up quickly. And in more recent years, another effect, some other effects I will mention later on, also provide not the strongest light, but also provide a way to enhance the signal. not because you increase the intensity of the illuminating source, but because you improve the signal detection. Only this. Okay, so typically then, your sample is illuminated. You can extract the light scattered by your sample. So you illuminate, you have a scattered light, you collect this scattered light and brings in a system we call monochromator. So there are mirrors or grating inside monochromators, and finally you get a detector. They are complicated monochromators actually. Some of them they have just one grating, some 2 gratings, some 3 gratings. And there are different mechanisms, mechanical mechanisms to drive this grating, to combine them. But this is a typical, let's see a little bit more detail here. You can see this is a typical, if you open up the box, it's something like this. When you buy today, you want a spectrometer, they just deliver a box to you. You put the box on the table and then just plug and go. But in the old times, we had to build the spectrometer in the optical table actually. Everything's open, right? So, but here you can see roughly a little bit more detailed. So you have here a light source, usually a laser, and then you can play with this laser to illuminate your sample. Then you have scattered light. So here you have some systems of lens to collect the light. Filters are very important in Raman spectroscopy. Very much important. Because many of the samples, they have a very strong fluorescence. Like for instance, biological samples. They all have strong fluorescence. And the fluorescence that comes from the sample is so strong that covers complete. And then what we do, we use some filters to get rid of those fluorescence. It's very important use of filters. And then this is this entrance slit of your monochromator. So the scattered light just gets inside, bounces around, gratings and mirrors until you have a diffraction and get your detector. These days we are using very sensitive detectors like CCD. CCD. So those CCD are very, very, very sensitive. So CCD is a technology that doesn't come so many years ago. Before CCD, we use photomultipliers. We are still using photomultipliers depending on the wavelength you're working. The system we have in my lab in Brazil, we have both CCD and also photomultiplier. Okay, now let's talk about a crystal or atom vibration or molecular vibration. Let's take the case of water. So we have hydrogen and oxygen here, and those atoms, they can vibrate in different ways. So we call this different normal modes of vibration. But typically you have a kind of symmetrical vibration here, which means the two hydrogen, let's say I am the oxygen and these two hands are hydrogen. So they vibrate like this. It's one way, symmetrical. Or they might vibrate like this. Or they also make like this. So those are normal modes of vibration of three atoms. Those of them are evenly. This is the case of water. And if you take another 3-atom molecule like CO2, so water is a 3-atom molecule, but atoms are in an angle. CO2 is also 3 atoms, but atoms are in a straight line, because carbon in the middle it has, in this case, hybridization, sp. Do you remember those stuffs from chemistry? Okay. So in this case, carbon is sp hybridization, which means you have here between one carbon and one oxygen, you have a sigma binding and a pi binding. Okay? Now, so how do these three atoms can move one with respect to the other? They have normal modes too. So now the situation is like this. The two oxygen can make like this. Okay? Or they can make like this. Okay? So they have normal modes of vibration too. Now, there are, of course, all this vibration, you can understand them in the framework of classical mechanics, right? So classical mechanics, you can solve equations of classical mechanics and then find all the normal modes. This is classical physics. And you know, the first proposal for classical physics was Newton's equation. But Newton's equation is something problematic because it is a proposal for one body only. It's a one body proposal. So if you have a system with many particles, then you need to disconnect all of them and check what is the interaction between all of them. So this is Newton is one body. And we have something similar in quantum mechanics. Schrödinger equation is equation of one body. This is what we call first quantization. If you are working with quantum mechanics with many body problems, then it's another approach, and that's why Feynman came along. So you have second quantization, and the Feynman diagrams is the framework to understand the second quantization. Here, it's similar. So the Newton equation is for one particle, and then for many particles came along, you know, Hamiltonian approach. So in the Hamiltonian approach is approach for many body problems in classical mechanics. The difference is in the Newton approach, you have to identify all the forces acting to each of the particles. And then you write down like this, you know, the net force is like the change, the time derivative of the linear momentum, actually. This is the way it was written. But in the classical Hamiltonian, you just need to write down the total energy as a function of kinetic and potential. That's it. So it may be complicated, but that's the way to make your approach. But if you do, like for instance, you can use for simple molecules, like 3 atoms or 4 atoms, small molecules, you can use Newton approach. Not very difficult. So you can write down this equation for each one of the atoms. Like for instance, this first one here, so you are looking at the oxygen number 1, and then the interaction between the oxygen is only with carbon. So that's the Newton equation for this atom. This is the Newton equation for the carbon. It interacts with both oxygen on the left and on the right, and that's the Newton equation for the right. So you can solve these 3 equations together, and then you find the normal modes. You can find the 3 normal modes for that one. So it's a way to write again those equations in matrix formulation, which is easy to come from the last to this one, and then you can find the normal modes. So that's the way you can formulate it, a little bit more complicated, but you can extract more information from it. And at the end, here are the 3 normal modes. So those are the typical frequencies of the normal modes. You can identify all the frequencies here. And you can do this for, let's say, not only the CO2, but you can do also for water. A little bit complicated for water because it's angle, okay? But you can really do it. So you have those three modes, what we call symmetric stretching, which is this one, okay? And then anti-symmetric stretching, which is this one. And the one we call translation. Everyone is moving. The whole molecule is shaking like this. So you get all the normal modes, and then you should expect, if you record the Raman spectrum of CO2, you should expect to see those normal modes. So you should expect to see three Raman lines in your spectrum. Let's say you take liquid CO2. If you want to do Raman scattering of CO2, you better take liquid because it's more molecules per unit volume. Okay, now so let's keep moving, and then it is typical if you see a Raman. This is a typical way to see a Raman spectrum. Here, the central line is actually the Rayleigh scattering. That's the wavelength of the incident light, your lasers there. And you should avoid to take this line into the spectrometer because the intensity is so high, and if that high intensity goes to the detector, maybe it's going to damage the detector. So you never scan your spectrometer crossing line. Please don't do that. Okay, now you can see that you have centered in the laser line or Rayleigh scattering, you have satellite lines, which are symmetrical in Raman shift. We call Raman shift, but intensity are different. So the higher intensity is the one we call Stokes scattering, and the lower intensity is anti-Stokes scattering. The intensity is different because in the case of Stokes scattering, the incident laser just creates one phonon. Anti-Stokes, the incident laser extract one phonon from the system. And the later case, the probability is much less. Okay? That's why the intensity is lower here. It's typical. So how do they connect to one another? It is typical that the intensity of the Stokes over the intensity of the anti-Stokes goes like this. And you can see that the intensity of the Stokes line is always higher than the intensity of the anti-Stokes line. And the higher the energy of the phonon that it creates or absorbs, the higher between Stokes and anti-Stokes, which means the lower the intensity of the anti-Stokes. You can see this, that not only in this term, but also over here. And also it depends on the temperature. If you increase the temperature, the exponent here just reduce, which means favors anti-Stokes scattering. This is one good point about Raman spectroscopy, because most of the spectroscopies we use, they are very sensitive to the temperature. And usually when you lower the temperature is the situation you can get more signal. But Raman is exactly the opposite. So you better don't lower the temperature of your Raman, which makes your laboratory, a little bit, cheaper. You don't need to invest a lot of money in cryostats and things like this. So Raman scattering, Raman, spectroscopy, you do at room temperature. No problem. Okay, now this is what shows you what means Raman spectroscopy. Any kind of vibration between atoms, it has a typical range of Raman shift or shift in the wavelength of the incident light. It is a sort of fingerprinting. Of course, if you have water, you have a typical Raman shift for water, for the modes related to water, typical. So, but let's say if you have water at room temperature, liquid, or water in ice, you will see a difference because the hydrogen bonding. So, any kind of bond that atom can do, it shifts a little bit, the vibration, and therefore it shifts the position of the Raman line. But actually it shifts inside a range. And this is why Raman is so interesting spectroscopy. Because if you have a molecule, any kind of binding that molecule does, you can check if using Raman spectroscopy. So this is a very important point. So Raman spectroscopy has this kind of feature. And you have books, books and books full of Raman line range. Any kind of family of compounds or solids, you have specific range of Raman spectrum. Sometimes it is, it's a time-consuming when you have your spectrum, and then you have to check one by one and try to find out which feature that comes in your Raman spectrum, which feature relates to your system. That's not easy task. I will show you some data taken from biological materials. You'll see how hard, you might guess how hard it is to, at the end, try to understand the whole spectrum. Not easy. Okay, now, this is a typical Raman spectrum. And I'm going to show you here, I'm trying to show two different scenarios of Raman spectroscopy, always related to nanomaterials. But in nanomaterials, you can just split in two important sides. One is a Raman from the core of your nanomaterial, which is crystalline, typically, is a solid. The other one is the Raman you can perform to analyze the coating of your nanoparticle. So typically you have molecules attached to the surface. Or sometimes you have your nanomaterial and then one molecule come outside and attach there. You can use Raman spectroscopy to modulate or to analyze this extra binding. That's what I'm going to show you. So in this case, this is a typical Raman spectrum from cubic ferrite. Typical. So it is the Raman in the core of the nanoparticle. Okay, so it's Raman from a crystal, actually. So if you look at cubic ferrite, then you will see that cubic ferrite belongs to this space group. And using symmetry, group symmetry analysis, you will see that you might expect 5 optical active Raman modes. So 1A, 2E, and 2T Raman modes. 5 Raman modes for cubic ferrite, typically. That's what says the cubic symmetry. And then, if you take Raman spectrum of cobalt ferrite, what you have is something like this. This is experimental. And in this case, if you do your deconvolution, you should do your deconvolution looking at what you should expect. And if you do the convolution of your spectrum in 5 components, you really found these 5 lines. You can fit nicely this spectrum. Though it may look a little bit noisy, but you can fit, typically. So this is one way to extract information of nanoparticles. And the difference between one and another here is that this sample is the sample it was prepared by co-precipitation. No treatment. And that one is the sample, the second one, is the sample you after. I'm sorry. This is the sample you obtain for co-precipitation. No extra treatment. And this one you make passivation. This is why this P is in here. It was passivated. And you can see the difference in terms of Raman intensity. The Raman spectrum here looks much. This one is much noisy. In the process of passivation, actually you cook your sample. Like you cook the bean. Exactly like this. It's sort of making a soup of your sample. And then the crystallinity of the sample in this passivation process just improves. And that's why you see a better signal-to-noise ratio in this case. It comes from the process of passivation. It's an improving of the crystal structure. Besides improving the crystal structure, this passivation process, it protects the surface of the nanoparticle. If you don't do the passivation like this one and keep your nanoparticles in suspension, maybe in 2-3 days you have nothing left. All the nanoparticles just dissolve. You need to perform passivation. So the passivation process not only protects the particle against bleaching, but also provides improvement in the crystal structure. And then it's clear to see in this spectrum, right? So the passivated sample has much better signal-to-noise ratio in Raman spectrum. And not only the Raman, it has influence on all properties of the sample. The magnetization is much better. Saturation magnetization is higher. Okay, so most of the properties, especially magnetic properties, improves when you do this passivation. Huh?
Passivation, how is it done?
It's like cook a bean.
Is it centric?
No. After you synthesize the sample, right, and then you extra boil the sample with some strong acid plus the salt related to that acid. Boil your sample in nitric acid. You should include iron nitride, for instance. And then you preserve the sample not to bleaching because of the strong acid. So in this case, the passivation was performed with nitric acid and iron nitride. And then you boil for hours, 3-4 hours, boiling. This is the passivation process in this case.
Going from low spin state to high spin state, then
it may happen because we have 2 different sites here, right? So in the passivation process, it may happen that you have change between iron 2 and iron 3. among, the tetrahedral and octahedral site. That may change the population between high spin and low spin state. May happen.
And that you can reveal through Raman?
Well, it's difficult to see in Raman. You cannot see this difference in Raman spectroscopy. Very hard to see.
Only magnetization can tell.
Magnetization and yeah, EPR you can see. In magnetic resonance, clearly you can see. Okay, now, this passivation process, for instance, if you do the passivation, you can investigate how your sample can age as a function of conditions you impose to the sample. So we investigate the aging of samples which were passivated and non-passivated. Or those who were passivated, they were passivated in different conditions. So we made all this investigation, and we found they are really very, very different. So here are some plots about the concentration. So you leave your sample to age in suspension, in solution, aqueous solution. Okay? And then time by time you just collect the supernatant. And then you analyze it in terms of composition. In this case, because it's cobalt ferrite, we used to extract some supernatant, and then we check ion and cobalt concentration, which means particles, how much the particles are delivering cobalt and ion to the solution. So it's a way to understand the aging process, how much ions the nanoparticles are losing to the medium. So we did this, and we found that the difference, a huge difference between passivated and non-passivated samples. So we prove how efficient the passivation process is actually. So it was a worth investigation, and then you really need to passivate samples if you want to use those materials for, some medical or industrial application. It makes your sample stable or not. This is the point. So also we use Raman spectroscopy, whole process. You can see that as the sample age, the crystal structure, actually those who are not passivated, the crystal structure is actually deteriorated. So you see the signal to noise ratio in the Raman spectra going lower and lower sample age if that is not passivated. So a very interesting way to analyze this process. Okay, the other way around is to look at the molecules which are attached at the surface of nanomaterials. Any nanomaterial that you synthesize and leave inside aqueous medium, immediately water comes at the surface and bind at the surface, especially if you have any metal in your sample. Any kind of metal oxide you synthesize in the nano range and leave inside aqueous medium, immediately water comes in and binds. This is a way to, it's a natural passivation process actually. Okay? Now, so, and then you might have a situation like this. This is the surface of your nanomaterial. Then the water just comes and binds in there. That's the first layer. But then comes the second layer of water around. And then you might have two situations now. One situation where the hydrogen is not bounded. The other one is the hydrogen bound is set in. So you have hydrogen bonded and no hydrogen bonded at the surface of your nanoparticle. So between the very first layer of water at the surface and the second layer. So Raman spectroscopy can easily distinguish between the two. So Raman bonding or hydrogen bonding and no hydrogen bonding. Let me show you. And of course, to understand the spectrum, you need to understand the Raman spectroscopy of water. Typically, no bonding water, you have 3 bending, like this, 3 bending, and 6 stretching modes, like this, 6 stretching modes. Okay? This is theoretically. If you go to experiment, actually what you can see is 2 bending and 5 stretching, typical. If you take the Raman spectrum of water, you see exactly this. Okay. Now, yeah, this is liquid water. You see stretching, the bending modes typically around 1600 centimeter minus 1, typically in this range, 1600. And the stretching modes goes up to 3400. So they are far apart to one another. Okay? And this is typical Raman spectrum of water. And you can see 2 Raman bending modes. We don't see 3. We see 2, actually. And if you look at the literature, it's the same. Nobody has seen experimentally 3 bending modes of water. And 5 stretching modes is typical. We searched in the literature and we found no paper that shows experimentally the 6 stretching modes in Raman, in the Raman spectrum of water. So here are the way the increasing energy. So the bending modes, the highest energy is this bending mode, very small in intensity. It's hydrogen bonded. The next to it, the next bending mode is no hydrogen bonding. You can see that the peak position is enough to be distinguished. Simple to be distinguished. Though the highest energy mode is just a shoulder. Okay. Then you have also hydrogen bonded. You can see the hydrogen bonded are higher energy. And then the lower energy are no hydrogen bonded. You have the asymmetric and symmetric stretching. Okay? And also then comes the partially hydrogen bonded. So water, one hydrogen is hydrogen bonded, the other one is not. So that's the Raman mode for this particular situation. So using this now, you can investigate materials which are not, which are nanomaterials with water around the nanomaterial. So this is the case for 2 cubic ferrite nanoparticles. This is copper ferrite and this is zinc ferrite. This is the wave number close to 1600, which is the bending mode, and this is the around 3400, which is stretching modes. This is water, this is copper ferrite, and zinc ferrite. You can see that water we could fit with 5 stretching modes, but those copper ferrite and zinc ferrite, only 3 modes here in stretching, though in the bending we still keep 2 modes. So now you may see in water you have 5 stretching modes, but if you have bounded water on top of you miss 2 stretching modes. And the reason is that if water is bounded to a surface of nanomaterial, it means it is not exactly water anymore. It's hydroxyl. One hydrogen is missing, And that side of the water molecule is binding to some metal at the surface. Now you don't have water anymore. You just have hydroxyl. And that explains why two Raman modes, stretching Raman modes, is just missing. Two of them is missing. Okay. And the bending modes, the two bending modes are still there. Why? Because hydroxyl is like this. Okay? So it can bend like this again, and it might have hydrogen bond or no hydrogen bond. It's the same as the pure water. But the stretching mode, you lose the chance to this symmetric movement, either bounded. So that's why you miss two stretching modes, and you don't miss bending mode. So this is typical. And then we see exactly what we expected. So 3 stretching instead of 5, and 2 bending exactly like water. So you can investigate this. You can, let's say now you have not only water, your sample, your nanoparticle or nanomaterial is not only suspended in pure water. Let's say you put an extra molecule in there, some alcohol. Then eventually that alcohol comes and binds to the hydroxyl, which is at the surface of the nanoparticle. Okay? Because the first layer around the nanoparticle is only hydroxyl. The second layer are pure water. But if you mix your water with alcohol, some of the molecules around will not be water, will be alcohol. And then the binding will be a little bit different. And you can see this in the Raman spectrum. Okay, which means it's a little bit of shift in your Raman position. So here is one example of one strategy to improve the orders of magnitude. And this is based in what we call near field effect. A near field is typically related to system that has a huge concentration of free electrons. So let's say a surface of a metal, you have a lot of free electrons, like metals like silver or gold or even copper. You have a lot of free electrons at the surface. So those free electrons actually, they create a very strong field, electric field, very near to the surface. This is what we call near field effect. So that strong electric field, if you go out of the surface a few nanometers, that strong field drops down very quickly. But if you have a molecule just approaching the surface, the interaction of that strong field with the molecule that approaches is very strong. That changes a lot all the properties of this molecule, particular properties that is related to the vibration. Okay. So I guess this year the Nobel Prize in Chemistry was about the near field. And the Nobel Prize in Physics was about the cryomicroscopy that I showed you yesterday, right? So the near field is, and then it was very important to Raman spectroscopy. So if you perform Raman spectroscopy of molecules which are attached somehow to surface which has a strong near field, then there is a strong enhancement of the Raman effect. The ability of Raman effect, the orders of magnitude. I'm not talking about 1,000 times. I'm talking about something like 10 to the 9 to 10 to 12 stronger. It's a huge enhancement. And that makes Raman a huge renovation of Raman spectroscopy. So that's why after the invention of laser, the second big step that helps Raman spectroscopy go even higher and use was this discovery of the effect of near field, because that provides a way to enhance the Raman sensitivity orders of magnitude. And that opened up a lot of opportunities. Here is one case. See, look at this experiment. That's a nanoparticle, typical. Here is a magnetic, but it does requires to be a magnet nanoparticle, any nanomaterial. Okay. Now we cover this nanoparticle with lauric acid. You know, lauric acid is what we call fat acid. It has a long chain of carbon. We represent like this, long chain of carbon. At the end, it has carboxyl group. This guy used to leave this one as hydrogen, and then the pair of electrons which is here just bind metal at the surface. That's what it does. So lauric acid is very good to surface coating nanomaterials if there are metals on this, such like metal oxide nanomaterials. So we coat this, and if you include lauric acid in a higher concentration, after it makes the first coating at the surface, just binding this oxygen to the metal, then comes to the second layer of lauric acid. And then the tail, the hydrocarbon tail, just bind like this. So it makes a double layer of lauric acid. This is important because at the end you have the carboxyl group here, which makes your nanoparticle hydrophilic. You can disperse in water. So then we came later on with this organic molecule, which is amphotericin B. Amphotericin B is a very strong drug to treat lung disease like tuberculosis. It's the first choice. It's the first choice. It's a drug of first choice to treat tuberculosis, actually. But amphotericin is very toxic, very much. Usually when the patient are taking amphotericin B, they need to host the patient in the hospital because the side effect is so strong. And usually they take this for about 6 months, between 6 months and 1 year. And then the patient needs to be housed in the hospital, which makes the treatment very expensive. So we try, for many years, try to develop some alternatives for delivery amphotericin B in a way that it reduces the toxicity. Because when you take amphotericin B, you have to take enough doses that part of that material goes to the lung in a doses that it is efficiently to treat the disease. But then the whole body, amphotericin B is in the whole body, which means it is systemic. So what is the aim of nanotechnologists? Make those drugs in a way that they can target exactly the organ. So this is one way. And I mentioned to you these days that whenever you coat any nanomaterial with DMSA, that material goes straight to the lung. What we did, actually, we double coating nanoparticles with DMSA and amphotericin B. So, one of the molecules, like DMSA, takes the nanomaterial to the lung, but it also brings amphotericin B. And once the nanomaterial has a magnet nanoparticle, you may perform magnetohyperthermia. When you perform magnetohyperthermia, the molecules attached to the surface just release. That's the trick. This is why we investigate the system. Okay? But now we need to understand exactly how the amphotericin B is attached. We know the surface, but how? Because the molecule is very complex. Which is the way, if we understand the way it is binded, then we can think about which range of temperature, which, what would be the best strategy to make the best drug delivery system. This is the point. So, the best way to understand how amphotericin B is attached to the surface was Raman spectroscopy, actually. Because Raman can track the change of the vibration of different groups in the amphotericin B. And finally, we found that is the way it is likely bounded to the surface. So we found no change on the Raman lines from all those groups of the molecule, but we found remarkable change on the Raman lines associated to the long chain. So we found, because lauric acid, in the middle it has a double bond. So that double bond is very interesting to track and to identify whether or not the chain is binded to any place. And of course we had to use the enhancement of the Raman line because of the near field effect. Otherwise you cannot see any Raman line. So the amount of material like this on top of the surface is not big. Besides, there is a strong background coming from the nanoparticle itself. So all this, it is against to see the intensity of Raman line, but the enhancement that comes from taking this nanoparticle and approach to a metallic surface like silver or gold. So it's amazing. What we made then was different substrates, metallic substrates, and then we just drop a solution of the sample on top of the substrate and leave this to evaporate. So the nanoparticles are sticky on the surface of the substrate. And then you can perform your Raman experiment. So that's the way. Let me see if I have some spectra here to show you. Yeah. Okay. Let me try to tell you what this is. So here you can see this is the Raman spectrum of lauric acid only, the first coating. Okay? Then you see the Raman spectrum of the nanoparticle coated with lauric acid. So what you can see, of course, you see typical correspondence of lines here, but also you see some extra lines, broadening, a little bit of shift. Of course, because those molecules are binding And also remember the double layer, one first layer is of lauric acid is around the nanoparticle. The second layer is binding to the first one. So the Raman line of this lauric acid now is much more complicated. But you can see this one. Okay, now comes the system that has like this one. Yeah. So this one here, this Raman spectrum is only amphotyrosine, pure amphotyrosine. It's powder. And the second one is let me see here, the legend. Yeah, the second one, this one here is only the Raman spectrum of the nanoparticle, only. And the middle is the Raman spectrum of the nanoparticle coated with amphotyrosine. So, amphotyrosine, pure amphotyrosine, and then amphotyrosine on top of the nanoparticle, which was double coated with lauric acid. And then this in the middle is the Raman spectrum of the whole system. Nanoparticle, double coating of lauric acid, and amphotyrosine around. And the last one is the difference between this one and this one. So we can see clearly that the difference between this and this one is exactly the amphotyrosine on top of the nanoparticle, because you subtract the lauric acid. And then if you analyze those peaks, actually you can find which kind of vibration in the amphotyrosine is related to those peaks. And then you see, okay, so this vibration just shifts. And then the amphotyrosine should be binding on top of lauric acid, exactly related to that ligand, that chemical bond. So that's the way you can get information to make a model of the way the molecule can bind at the surface of this nanomaterial. So this is very helpful. If you try to do this without using the near field of any metallic substrate, you see nothing, absolutely nothing. So this is the way, and this higher near field is so interesting. Let me show you the next one. You'll see. So this is another example of using this enhancement called SARES, which is surface enhancement of Raman spectroscopy. That's the acronym of surface enhancement of Raman spectroscopy, SARES. Okay, look at this experiment. So here is a sequence. This is the pure nanoparticle, and that's the nanoparticle coated with probably lauric acid, the same thing, and then comes amphotyrosine on top. This nanoparticle was injected in the mice. It goes to the lung. We extracted the lung after some days, and then we perform Raman spectroscopy in pieces of the lung. So, and you may guess how complex would be the spectra of a piece of a body. It is very much complex. Okay, that's the way. And then those animals were killed after some time. We extract pieces of the lung, and then we deposit them on top of the substrate, metallic substrate, like gold and silver. How we made them? We made them by electrolysis. It's simple to do. Okay, now look at the spectrum. Those are the spectra. Though you may say, wow, how can I see something in there? Okay, it's not easy. But you can see important differences. So let me try to tell you which one is this one. But this one, they are all pieces of lung. All. The difference is this one was no infected animal, which means animal that diseases in the lung. We have animal with disease and animal without disease in the lung, and we inject in both. So this is no infected animal, and then it was injected just PBS. PBS is a typical solution, biological solution you use to inject, as a reference, actually. So these are no infected animals injected with PBS, infected animals injected with PBS, treated with PBS. And you can see difference here. The difference is because the infected animal has lung already damaged, and the cells are different. And what you see here is the difference in the cells from the lung, actually. And you can see, you can use this one and say, okay, if you take a sample of a lung, and then you can say whether or not that lung is infected. Here is the difference. You can modulate this carefully, line by line, and check the intensity and the Raman shift. We did this also. So you can say, you can use this Raman spectra to make what we call the follow-up of any kind of treatment. We made this with cancer recently. Okay. Now, this one is infected animal treated with nanoparticle not coated with amphotericin, just the double layer of lauric acid. Then comes the difference. Now is infected animal treated with amphotericin, free amphotericin. Okay? So just inject free amphotericin in the animal. And this is the infected animal treated with nanoparticle coated with amphotericin. Okay? So we were able to analyze all this line by line, intensity, Raman shift, and the final conclusion was the difference between animals, infected animals, treated with free amphotericin, which is the normal treatment, the one which is very toxic, the one the patients need to be housed for 6 months, 1 year in the hospital. And this one is the treatment with nanoparticles coated with amphotericin. At the end, what was the conclusion? The conclusion was we can treat the animals and having the same outcome of the treatment with 40% less concentration of amphotericin. So, if you put amphotericin on top of the nanoparticle and inject that one, you can use 40% less concentration of amphotericin, almost half, which reduces the toxicity. Also, you have the same outcome if you perform injection every 72 hours compared to every day. So free amphotericin, you have to inject every day. Okay? Amphotericin on top of the nanoparticles, you may inject every 3 days. It's a big difference. You reduce 40% in concentration of amphotericin, and instead of everyday injection, you have every 3 days. So that is the difference. And what is behind this? I didn't show you here, but I told you before, not only amphotericin was placed on top of this nanomaterial, but also DMSA. Because DMSA is the guy who drives this nanoparticle to the lung. So you can reduce the doses very much. It's 3 times plus almost half. So it comes roughly about 5 times at the end. It's 1/2 of 1 order of magnitude. So that gives you the same outcome of treatment. All this conclusion actually came from Raman spectrum analysis, nothing else. So I hope I was able to convince you that Raman spectroscopy is extremely interesting, useful, and still going up. And you can use it everywhere. Sometimes it's not easy to analyze the data. But once you find a way, a protocol to analyze your data, it's extremely useful. Thank you so much.
Sir, in one of your paper, SERRS is mentioned. Instead of SERS, SERRS is mentioned. This one. So what is this?
Oh, this one is a variation of SERS. He was talking. He's talking about this one here.
Yeah, this.
Yeah. There is one extra R, and this one is only 1 R. One has 2 legs. Another one has just 1 leg. The extra leg is resonant, surface enhanced resonant Raman spectroscopy. Because sometimes you can use the laser line very near, very close to the Raman absorption. Okay, so that's the way it enhances even more. Actually, this is the point. So the resonance Raman is even more intense. It magnifies.
Raman spectra of ferrites. No nanoparticles, no suspension, just solid particles.
Yeah, there are. If you look at the literature, there are lots of Raman spectra on normal Raman and single crystals. A lot. People use this a lot at the beginning.
Even for ferrites, we can see.
Even for ferrites.
There are no OH or such things. These molecules, are they Raman active?
Well, no. In cubic crystals or in bulk crystals, the surface, of course, usually when you are going to perform any spectroscopy in materials like that, oxygen in atmosphere is very bad, so it oxidizes everything. It coats, you better clean the surface first. We do this. So if you want to perform any, technique that has incident light in your sample, you better clean the surface. It's a way to clean. You need to clean the surface. It's a good way to do it.
Small doubt. If my understanding is correct, you want to use Raman spectroscopy as a diagnostic tool in medicine.
Yeah.
But the thing is, I think all rats were killed. All rats were killed. But how can we use it for human beings?
Yeah. You're right. So it's very interesting. He touched one point very, very interesting in modern medicine. We are in a day that we want all kinds of medical treatment. No pain, no invasive. So we want to, have no pain, and then we enter a machine. The machine doesn't touch us at all, and at the end, the output tells everything which is right or wrong with you. Okay, so this is normal. This is human being. We are moving to this. Yeah, actually, we are moving to this. So everyone, those groups, those research, or companies which are working on this, they are very much worried all the time to develop technology that is non-invasive, and any kind of treatment you can take which doesn't give you any pain. So, it is possible to develop Raman or any kind of, analysis, diagnosis without being invasive. But I can tell you, until you get this point, unfortunately, many animals will be sacrificed. That's the way, unfortunately. There is a huge trend in biology these days trying to simulation in biology. It is one trend that try to answer this question and try to minimize the number of animals which are sacrificed every day. Because I can tell you, it's a lot. It is getting lower and lower, more and more difficult to work with animals. If you go in US or Europe, it's very difficult. Every day the regulations are going very tighter and tighter. Like for instance, these days, if you want to perform experiments with monkey, in US, almost nowhere anymore. In Europe, the same. So some countries in the world still are doing, they have regulations which allows you to do. Brazil is one. But we have only 3 facilities in Brazil that can perform experiments with monkey. And my university is one. We have one in the Northeast, one in the middle, and one in the South. Only 3 left over. 20 years ago, it was much more. So that's the normal trend. But today, for instance, you can perform, let's say, in your blood, you can put a sensor here, optical sensor, and it can analyze your blood without punching yourself. Okay? So they are using, for instance, photoacoustic spectroscopy to make this, to analyze your blood without any invasive procedure, actually. It is developing like this.
Magnetoencephalography is also there. Magnetoencephalography is there.
Yeah, it is. Yeah. But that's the way. So we don't want to be in pain. Nobody likes that anymore.
Can we take a break now?
Oh, yeah, sure. Thank you.